Okay, so good morning, everyone. So last meeting, we discussed about nucleons. So nucleons, and it is comprised of two nucleons, which are protons and neutrons. And then we discussed isotopes as well. So isotopes are atoms with same elements but different mass number due to different numbers of neutrons. And we discussed about types of radioactive decay. We have alpha decay, beta decay, positron emission, gamma emission, electron capture, and then aside from that, I've also given examples as well. And today I'm going to discuss the neutron to proton ratio. So neutron to proton ratio, any elements with more than one proton will have repulsions between the protons in the nucleus. And there is a strong nuclear force that helps keep the nucleus from flying apart. Now, because neutron being a stable or a neutral particle helps in binding the nucleus together despite the additional proton. Therefore, neutrons play a crucial role in stabilizing the nucleus. Therefore, the ratio of neutrons to protons is an important factor. So here on the right side of your screen, so here we have this graph. So on the x-axis, we have the number of protons, and then on the y-axis, we have the number of neutrons. So the thin red line, this is the 1:1 neutron to proton ratio. And then the red shade here, so this is the belt of stability where nuclei are stable. So we have zircon, tin, we have Hg. So with those elements having their atomic number and atomic mass, they are stable. So for smaller nuclei having an atomic number of um less than or equal to 20. So these are stable nuclei, and their neutron to proton ratio should be 1:1. Okay. So since as shown in this graph, the 1:1 ratio intersects with the belt of stability at atomic number 20 or less than. So to so those smaller nuclei only with atomic number 20 or less than 20, and their neutron to proton ratio should be equal to 1, to make them stable nuclei. And as the nuclei gets larger, so above 20, it takes greater number of neutrons to stabilize the nucleus. So if we compare this line here and this belt of stability, so as you notice, it needs a lot of number of neutrons, right? Because here is the number of neutrons. So it needs a greater amount of number of neutrons so that it'll reach the belt of stability, which are nuclei with stable that are stable. And the shaded region in the figure shows that nuclei is stable, and it's called the belt of stability. So the nuclei above this belt, they have so many or too many neutrons, while they tend to decay by emitting beta particles. So these nuclei, the nuclei that is located above the belt of stability, they undergo beta decay. Meanwhile, the nuclei below the belt, they have so many protons, so they need, in order to become stable, they need to undergo positron emission or electron capture. And there are no stable nuclei with an atomic number greater than 83. So yung mga elements with atomic number greater than 83, if you look at your table of elements, so we have bismuth, polonium, and astatine. So those elements, hindi na sila stable. And these nuclei tends to decay by alpha emission. Large radioactive nuclei cannot stabilize by undergoing only one nuclear transformation. So they undergo series of decay until they form a stable nuclide, often a nuclide of lead. So for example, we have uranium here. So series pa ng nuclear reaction ang kailangan before siya ma-stable. So the uranium undergoes alpha decay, and then it undergoes series of decay to thorium, to radium, radon, polonium, para maging stable na siya, which is, in this case, lead. And nuclei with 2, 8, 20, 28, 50, 82 protons, or 2, 8, 20, 28, 50, 82, and or 126 neutrons tend to be more stable than nuclides with a different number of nucleons. So these numbers, they are called magic numbers because these nuclides with these number of protons and neutrons are stable. For example, we have for 2, we have helium, right? Helium has a proton that is 2. And then for oxygen, oxygen has number of proton of 8. So those elements are stable. And then nuclei with an even number of protons and neutrons tend to be more stable than nuclides that have odd numbers of these nucleons. So here, for those elements or nuclei with with the number of protons that is even and number of neutrons that is even as well, they are stable compared to those nuclei with odd number of protons and odd number of neutrons. For example, which of the following nuclei are especially stable? You have helium, calcium, and technetium. So for helium, it has a number of proton of 2, and it has a number of neutrons of 2 as well. That's why it's stable. And aside from that, it is included in the magic numbers. So helium is stable. And then for calcium, it has number of proton of 20 and then number of neutrons 20. So it's stable as well. Meanwhile, technetium, it has an odd number of proton, which is 43, and then its neutron is 55. So it's not stable. Therefore, the following nuclei that are only stable is helium and calcium, are helium and calcium. So next, which of the following nuclei are specially which of the following nuclei would you expect to exhibit a special stability? So we have tin, astatine, and lead. So for tin, the number of proton is 50, and then the number of neutron is 68. So it's stable because both are even. And for astatine, we have 85 and 210. So the number of neutron is 210 minus 85, 125. So it's an odd number. So astatine is not stable. Meanwhile, lead has a number of proton of 82 and the number of neutron is 126. So it's stable. So the following nuclei that is only stable is tin and lead. Now next, predict the mode of decay for plutonium and indium. So um, we'll be answering, or we can answer this exercise with the following lesson. So nuclei above this belt have too many neutrons. So that's why they need to undergo beta decay. So if we go back to this question here, predict the mode of decay of plutonium-239. Okay. So plutonium-239 is not included on this graph here because the atomic number is only limited to 80. However, we discussed a while ago that for atomic number which is greater than 83 here, they will undergo alpha emission. So therefore, the answer for this one is the mode of decay for plutonium-239 is alpha emission. And then for indium as well. So indium has a mass, indium has an atomic number of 53. So if we look at this graph here, 53 is the number of proton, and then so its number of neutron is 120 minus 53 is 60. Okay, 120 minus 53 is 67. So the number of neutrons is 67, so it is here. And then the number of proton is 53. So I think it's located here below the belt of stability. And as what we've discussed, if it's below the belt of stability, it should undergo positron emission or electron capture. Okay, now we're on slide 42. So you need to familiarize this table. So for atomic number greater than 83, we have alpha decay, and for atomic number 1 to 20, with a ratio of with a ratio in neutron to proton that is greater than 1, so they should go beta decay. And if their atomic number is 21 to 40 and their neutron to proton ratio is greater than 1.25, again, they'll undergo the beta decay. And then for atomic number that is 41 to 82, with neutron to proton ratio of greater than 1.5, they still included in alpha decay. So they'll undergo alpha decay. Meanwhile, if they're for nuclei that has an atomic number of 1 to 20, but their neutron to proton ratio is less than 1, so they'll undergo positron emission. And then 21 to 40, that which has a neutron to proton ratio of less than 1.25, they'll undergo positron emission as well. And then for 41 to 82, which has a neutron to proton ratio of less than 1.5, they'll undergo positron emission or electron capture. So be familiarized with this table. So this is your assignment to be submitted tomorrow, Thursday. And then we have nuclear transformations. So they can be induced by accelerating a particle and colliding it with the nuclide. And this is a particle accelerator. So these particle accelerators, they are enormous, having circular tracks with radii that are miles long. And let's discuss about the kinetics of radioactive decay. So kinetics will obey this equation here. So kinetics is the study of rates of a chemical reaction, and it focuses on understanding how and what speed chemical reactions occur. So this here is a first order process, and then it has an equation of ln NT over NO equal to negative KT. So NT is the final and NO is the initial. And negative K, or K is the decay constant, and T is time. And then this is the equation of half-life as well. 0.693 over K is equal to T. So half-life, it is the time it takes for the half of the atoms in a sample of radioactive substance to undergo radioactive decay. So for example, if you have a full molecule, so it is the time that is needed para ma-half siya. So that's half-life. So let's have an example. A wooden object from an archaeological site is subjected to radioactive dating. The activity of the sample that is due to carbon-14 is measured to be 11.6 disintegrations per second. The activity of a carbon sample of equal mass from fresh wood is 15.2 disintegrations per second. The half-life of carbon-14 is 5,715 years. What is the age of the archaeological sample? So, sabi daw sa question, may wooden object na nakita daw ng mga archaeologists. And then, that wooden object is carbon-14. Tapos, mineasure nila yung activity ng wooden object na yon, and then nakita nila na may 11.6 disintegrations per second siya. Tapos, after that is, gi-compare nila sa fresh na carbon sample, which is from fresh wood, and then may activity siya of 15.2 disintegrations per second. Tapos, ang half-life daw ng carbon-14 is 5,715 years. Ano daw ang age ng sample na nakita ng mga archaeologist? Okay, so using the half-life equation, we can get the decay constant. So, plug in lang yung half-life, which is 5,715, and then makuha mo na yung decay constant. This is your decay constant, 1.21 times 10 to the negative 4 per year. And then, using this equation here, so substitute the value of K, which is 1.21 times 10 to the negative 4, and then yung initial mo, NO, is yun yung sa wood, na fresh wood, which is 15.2 disintegrations, and then yung NT mo naman is yun yung nakita sa mga archaeologists, which is 11.6 disintegrations per second. So substitute all the values, and then you can get the age of the wood. So it's in years, so 2,235.5 years. So that is the final answer. And then another example is a rock contains 0.257 milligrams of lead-206 for every milligram of uranium-238. The half-life of the decay of uranium-238 to lead-206 is 4.5 times 10 to the 9 years. How old is the rock? Okay, so yung currently daw, yung rock is may lead-206 siya for every unit of uranium-238. So find the age of the rock. So presumably yung lead-206 mo is dahil nag-undergo siya ng radioactive decay from uranium-238. So nag-form siya ng lead-206. And then let's apply the first order kinetics in the equation. Then after that is we will calculate the initial amount of uranium-238. So let's solve. So find first yung original quantity, yung original mass ng uranium. So, di ba, sabi is currently for every 1 milligrams of uranium-238, may 0.257 milligrams of lead-206 ka. So, 1 plus 0.257, and then multiply it to the molar weight of uranium over the molar weight of lead. So, makakuha mo na yung original mass ng uranium, which is 1.297 milligrams. And then, you can also get the decay constant. So, di ba yung formula ng decay constant is this. Kasi may given siya na half-life. So, you can get the decay constant. So 0.693 over the half-life, 4.5 times 10 to the 9 years. So this is your decay constant, 1.5 times 10 to the negative 10 per year. And then, isolve na natin kung how old yung rock daw. So using the first order kinetic equation, which is this one here, so we can get the time, how old is the rock. So, substitute lang. Yung K mo is nakuha mo kanina, and then yung NT mo, which is the final mass ng uranium is, di ba, 1, and then yung initial is 1.297. So, makukuha mo yung time. So, this is the age of the rock. 1.7 times 10 to the 9 years. And then another example, if we start with 1 gram of strontium-90, 0.953 grams will remain after 2 years. What is the half-life of strontium-90? How much strontium-90 will remain after 5 years? What is the initial activity of the sample in Becquerel and Curie? So Becquerel and Curie, they are units of activity. So si Becquerel, Becquerel is equal to 1 disintegration per second. It's named after Henry Becquerel, who discovered radioactivity. And then si Curie naman, Curie has 3.7 times 10 to the 10 Becquerel. So, or 3.7 times 10 to the 10 disintegration per second. So it's named after Marie Curie in honor for her discovery with radium. Okay. So let's find first yung half-life of strontium-90. So using the first order equation, substitute lang, may time ka na given, and then yung final N mo is 0.953, and then yung initial mo is 1 gram of strontium. So makukuha mo na yung decay constant. And then, after you get your decay constant using the half-life equation, makukuha mo na yung half-life, which is 28.8 years. So we're done with letter A. And then for letter B, how much strontium-90 will remain after 5 years? So after 5 years, so using the first order equation, di ba may value ka na sa K, yung nakuha mo kanina. And then yung T mo is i-change mo lang to 5 years. So para makuha mo yung NT, so kunin mo yung NT. So if we calculate NT, so NT now, yung natural log mo is dapat ilabas mo yung NT sa natural log mo. So para malabas siya is gawin mo yung right side in exponential. So yung value mo is raised sa exponential. And then makuha mo na yung NT. 'Di ba kasi yung NO mo is 1 gram. So substitute, makuha mo yung NT, which is 0.887 grams. And then for the letter C, so using yung decay constant mo, so you need, di ba, yung nasa decay constant is per year siya. So change it to per second para ma-cancel siya later. So change mo na yung K from year to second. So, and then after that is, di ba, yung initial mo is 1 gram. So, yung 1 gram is convert mo siya to number of atoms of strontium. So, para ma-convert siya is multiply mo siya sa molecular weight ng strontium, which is 90 grams per mole. And then, multiply mo siya sa Avogadro's number, which is 6.02 times 10 to the 23 atoms strontium per mole. So, makuha mo na yung number of moles, I mean, yung number of atoms mo sa initial sample mo. So, yung total disintegration is yung K mo, this is your K in seconds. So, it can be written in per second or it can be written in disintegration per atom per second. Then, multiply mo siya sa number of atoms. So, ito yung total disintegrations. And then, kasi yung hinahanap is in becquerel and in Curie. So, di ba, 1 disintegration per second is equal to 1 becquerel. So, this is also your answer in becquerel, 5.1 times 10 to the 12. And then in Curie naman is use this conversion. So, 3.7 times 10 to the 10 disintegration per second per Curie. So you can get the activity in Curie. So you have 1.4 times 10 to the 2 Curie. So that is your answer. So that ends this meeting.